about me. My name is Petr Chalupa. I work at Red Hat and I'm kind of a Ruby enthusiast, so you can tell from this. By the way, this is kind of example from a library I'm trying to implement, actor model implementation for Ruby. So this is probably how it will look like, and I hope I will be talking about that later. Another group and Pyvo. Okay, so just before I start to talk about actor model, why such things exist. When you try to do some low-level cryptocurrency, as my colleague mentioned, it's hard. You have the basic thing is that you have some synchronized block. This is example from Ruby, and only one thread can enter this synchronized block, or it's called critical section. But it's really hard to get it right or reason about, because you don't know every possible state in which the application can be. So you always forget something and you get deadlocked bugs, and it's also you don't have a way how to find it easily unless you can unless you can get some continuation. You can do that in Smalltalk, you can't do that in Reveal. I don't think you can do that in Python. It's also very hard to test because you have no way how to simulate that your application goes through all the possible ways and the threads are scheduled in all the possible orders. So it's just terrible to work with. Just out of curiosity, how many of you did ever work on this level with concurrency or parallel programming? So you probably know what I'm doing, right? It's hard. So, and it always fails in production, never in development. So we need something better. My colleague already talked about that. Really useful is future objects. The one my colleague described are for Python. This is implementation I did, so the methods are called something different. You resolve is for setting the successful computation of the value. Fail you would use for setting the future for some exception. There are some checking methods. You can check it's ready, which means resolved or failed, or you can specifically check if it was resolved successfully or it failed. You also have two blocking methods. If you call the future with method wait or value before it's resolved, your thread will block until the future became resolved. So this is useful for things like this. Did you ever heard about function pmap? It's a shortcut from parallel map. It's from, I think it's in Haskell or in Clojure. Okay, so because many of you don't know Ruby, so this map function allows you to map some function on each value of array data. So when you call map on it, and you can create a new future. That is just a helper how to work with the newly created future and we store it in the f variable. So you can create thread to do computation for over each value and just return the futures object immediately. So in the end, when you set up all the computation for each of the values in 3 threads, you would call each and call value. Sorry, actually I have a bug here. that should be mad because you need to get the value. So at the end, you have set up all the calculations and they are running on the background, and you call map and method value on each of the futures, and it will block until all computations are done. Okay. So this is just a simple implementation. How would you do parallel math or math? Okay, and as I was talking at the beginning that the low-level synchronization and stuff like that is hard. So this is just a small example taken from the future implementation I did. So this is method do then, which is, I forgot how it was called in the Python, but it allows you to schedule some block of code to be executed after the future becomes resolved. So the future object has some lock in an instance variable stored, and the difficulty is that you have to think what has to be in the log, in the synchronized block, and what can't. So in this example, you have to store these texts in this log, because if you wouldn't, some of the blocks can leak out, because in the meanwhile another thread can resolve the future and the block would be never executed. So you have to lock it. But the blocks also can take some time, so it's a bad idea to, when the future is resolved, to call these blocks inside the synchronization block, because you would prevent all other threads to just check if the future is resolved, because the log is global for this instance of future. So you have to do this outside, so another threads can check if the future is already resolved or not. And stuff like that you have to really think all the time about, so you don't want to do this. So, yeah, and another example why this is hard is, how many of you know what volatile, I don't even know how this is pronounced. Who knows?
Is it like
volatile?
What?
Is it like in C?
Yeah, but it's also in Java. In a Ruby, the standard MRI implementation, you don't have to care about this, and I think we don't have to care about this in Python, because it has the same thing. But before we get to that, how many of you know what volatile means? Okay, so volatile means that you can mark variables in C or Java that you will be accessing them from many threads, and it basically means that all the threads are always having these variables synchronized in their register, execution register. So it can happen that one thread is reading another value than another thread. If it's not marked as volatile, it can happen that when you assign some value in a variable, some thread will see the variable, will see the value, but another will not. And this become important when you try to implement some libraries to run also on JRuby. And on JRuby, you don't have guaranteed that instance variables are volatile. So you have to synchronize each instance variable, each access to that, so you can be sure that all the threads are reading the same values. That is really messy. Just another thing why this is hard, and you don't want to use just synchronized blocks and critical sections. So finally we are at the actor model. So you can think of actor model as, if you want to organize your code, you use objects. If you want to organize somehow your parallel execution, you would use actors. And actor is basically some computational entity. And the basic behavior is that actors are receiving messages, and it can react to received message by creating finite number of by sending finite number of messages to another actors, or it can create a finite number of new actors, or it can change its internal state, so it alters the behavior to the next message it receives. So this is.
Can I ask something?
Yeah, I just finished 2 sentences. So this is taken from Wiki, and I would do this 2 important corrections here. That if you are trying to do something like that in a Ruby, Python, or any language that basically doesn't really care about immutable data structures, the important thing that you send always immutable messages, and the whole state of the actor is really encapsulated, and you can not read it directly from another actors. So if you want to know anything about some actor, you need to send him a message and wait for some response to read the information.
So the ballet of designing the behavior of Lola. So that means that generally that object, that actor just react to one kind of messages, or
No.
But it can change its own behavior, how it will react to some messages.
Yeah. In Ruby, the implementation would look like that you have some method on message, and you will get a message, and then it's up to you to implement what do you do on each kind of the received message. So this is basic. Do you have any questions about this description or? Okay. But why does this? How does this work that it's actually useful for something? So this is not every library, actor model library, implements this. But for example, Erlang OTP does. And it structures its code by creating something supervision trees, and it means that you create the first actor, so it's called process in Erlang or whatever. You spawn a first actor, and you start to create, I don't know, my web server, my workers, and things that you need to do in the application. And you monitor these other actors that they are still alive, and when they fail, it's up to the supervisor to restart them or kill a whole bunch of the actors and restart them all together. So you delegate, you just let. If there are bugs, you let them crash and restart it from the beginning. Nothing. Yeah, linking is another pattern. You can mark. Let's say you have a bunch of workers, and they are in some state, and they are sending messages between each other. And if one of them fails, it could be really hard to determine what to do next, how to heal the failed actor and to fix the bug. So the easiest thing is just to kill all of them and start them from the start with the correct state. So this is, you link them together. When one of them fails, everything. And also to make it more simple, the libraries usually implement that you can send messages asynchronously, synchronously, or to get the future. Meaning that if you send it asynchronously, you just send the message, forget about it, and you are continuing with the computation in your own actor. If you send it synchronously, your actor will block until it will receive a result. But this can be really dangerous, because if you do this enough times, if the actors are implemented over some thread pool, you can run out of threads, and basically the application stops. And this is not a good idea. You should avoid it, or do it only when you are really sure that you will get the response fast. And future, it's just if you need to monitor when you get the result, or do something like that with it later. Okay. Also, the description I gave you before, this was a basic definition from the wiki. But the actor model libraries are very different, each one from another. There are many ways how to implement that. Also because not every language is allowing you to do some fancy stuff. So I'll just brief. This is important to know when if you want to do something, some parallel computation, and for example, each actor can run on its own thread, or it can run in a coroutine, or it can run over, let's say, all your actors will be running over some pool thread, global pool thread in your application. And you need to know, because if you are, let's say, creating 10 threads for each user connecting to your application, and the actors are spawning threads, real system threads for each, you will run out of memory very soon. Because thread is really heavy, the stack of the thread, I don't know how big is, but I did some tests and it was failing for 2000 threads on JV already, so it's just a limit, big limit. But it can differ if it can be event driven, or the actors can have stack, meaning that the actors can be implemented by they are just having some on a message method, and the method is called every time it receives a message, and when the function ends, the execution of the actor ends, and another actor can use that thread. Or if it has sorry, but this is important. If you have this, you cannot use things like you saw before in the previous presentation, that there was a coroutine and there was a yield, 2 lines, first yield and the second. You can't do that in this. If you want to, you would have to do the same stuff with the callbacks. You would have to create other functions and stuff like that, because you don't have the stack to return to after you get another message. Okay, so also there is information that some actors have some life cycle that they are started, they can be paused when there is some error, you have to explicitly terminate them, or there are some implementations that they are just garbage collected when the reference to them is lost. So you also have to be careful about that. If the actor is shielded, we have some implementation that if you create by mistake a public method on the actor, you can just access it and alter its internal state, and that's just way too hell, because you are now. That is the main thing why you choose actors not to do this. Okay. And yeah, so that was just brief mention how you could get around if you don't have actors implemented with stack, meaning with the thread or coroutine. So you can use something like unbecome and become. So you can use become and set another conditions of which messages are able. I don't know. You start an actor and you specify that it will receive only message A and B. But if you need to compute something complex, and let's say you need to receive message B and C in order to be able to compute something and then send another message to another actor, then with this, when you receive message B, you call became, and it will specify that now, from this point on, you will be only receiving messages C. And this actor, will be now waiting for message C and storing all other messages in mailbox until it can compute the results and message D, and then you would call undecam and start behavior as at the start. So there are ways how to get around that your actors don't have stack or they are not implemented as authority. Or if they are, you can have the implementation of the actor is just one function or many functions, and then you have the stack, and you would call blocking the receive method on some points. And so the example before, you need message B and C. If you have blocking the receive access in this implementation, you just call receive B, receive C, and send B to C, and you are done. Just very simple. So yeah, if you have it's implemented with thread, you have some limits, so you have to be careful about that. And on the other hand, if you don't have this limit because your actors are implemented over some pool, and you need to do some I/O. So usually libraries are implemented that when you do some I/O, it will block the thread until you get the response. But if the threads are actually from the pool and your actors are doing the blocking I/O, you can also have to be careful because you can run out of the threads from the pool because all your actors which are now executing are blocking and waiting for the I/O. So this is another thing you have to consider. But it's still better than just the critical blocks. But it's not the silver bullet. I wanted to mention some libraries out there. So maybe the most famous one is Aka, which is originally for Scala language. It's the version that it has lightweighted actors, meaning that there is a pool. It has control over the state, there is stars linking, all the fancy stuff. And also it has interface, so you can use it from Java and from JRuby, so that's what I'm mentioning. Also, in Ruby there is one existing implementation of actor pattern, but this is really a hybrid one. So it actually, what it does is that it spawns real thread for each actor, and then for each received message, it spawns another fiber in that thread. So I don't know. Somebody thinks it's that smart. I think that's I would. Because the main idea of the actor is that you have the isolated state of the actor and you are receiving the messages in sequence and you have control over it. If you do this weird stuff, then when you receive the message, you spawn one fiber. And at some point you will start waiting for some I/O, so it will yield. Another message is received and executed in the same object, but it has access to the same variables in that object which are not in a, I don't know, coherent state because this computation before didn't end it. So, I don't know, it's just stupid. So, and there is, I found some implementation called Clicker for Python, but I'm not in Python, so just...
It's very shitty.
Okay.
For someone who used Erlang before and after.
I believe it.
For someone who used to Erlang with any other actor from that distribution?
Yeah.
Just tried in Python and
maybe you can say something more about it later. But Pika is you can use thread per actor, so you have the limit of how many actors you can spawn. Or there is some implementation with Greenlands, you mentioned it. but you can't mix it with real threads. So I don't know. It sounds very limiting to me. So it wasn't that. And in the end, OTP library, which is from Erlang. I'm not sure about it, but I think that Erlang is the reason why this is so fancy now, implement model, because and well, this is implemented in every language. But Erlang is really very different from other languages, and because, for example, it's just some facts. I don't think you do have access to threads, real threads in Erlang.
No.
No, I don't think so.
You are using Erlang processes.
Yeah.
Which are
The Erlang is use as many threads as you have cores under the hood, and allows you only to spawn very lightweight threads. It's called processes in Erlang, which is the feeling of using it is the same as thread in another language, but it's very lightweight and you can do, I don't know, 1 million of them, and it's not the problem. It has its own scheduler. It's also directed to be real time, so when the scheduler does it, only allows, I don't know, about 1,000 reductions, because it's a functional language, so the reduction is a computational unit. So it only allows you to do 1,000 reductions, and then it moves to another process. It's very lightweight, and because it was originally intended only for embedded systems like switches and I don't know, stuff like that. So it's more like OS operation system. So also there's very interesting project Erlang on Xen, where you can run Erlang virtual machine directly on Xen virtualization, and you don't need any operation system to do that. So it's very fast. By the way, if you know language Elixir, you can also do that with it. But just I'm starting to have feeling that
I recommend Elixir for like Python and Ruby programmers. It's much easier than raw Erlang.
Definitely.
You are welcome.
Yeah, but even if you are using this awesome library or Erlang, there are still some problems. There is no solution which for everything. So even if you are using Erlang or some very good implementation of actors on another language, you have to watch out, I don't know, for things like if the library allows you to do receive just on some specific message. As I was saying, you are receiving only C messages. If the actor is very busy, it can have, I don't know, 1,000 messages waiting in its mailbox. And if you call receive C, it usually goes and iterates over whole mailbox. So it is getting slower and slower. So you have to be careful when you are doing this. Also, you can, if you have a big system and you have only one actor which is intended for logging, it just at some point it stops keep up, and your mailbox starts growing faster than the logger is able to log the messages down. So you can run out of memory and your VM crashes and dies. So you have to monitor your system. There's a rule for everything, but you just have to do it. At the beginning I mentioned that I will be talking about another stuff, but before I get to that, do you have any questions about actor model?
I would just have one question.
Okay.
What you were trying to implement when you were like very decided to use actor model pattern?
I'm trying to implement actors, lightweighted actors over thread pool or Ruby, because threads are heavy, and for my particular case I need to create a lot of them and very often, because not just that the thread is memory consuming, it also takes time to create one. So if you have actors which are don't spawning threads for every instance, you can spawn and forget about a lot of them. It's much faster, and that's the case I need it. So I'm working on the lighter implementation for.
And you needed this implementation
For a project, it's called Dimeflow. It's a workflow engine. We are using that Red Hat for a project called Catalog, which is plugin for Foreman. And
yeah, so you are working on Catalog.
Yeah.
Max Satellite.
Yeah, so that was the satellite.
Thanks.
Okay, just one question. Would you use actors? Was this positive, that it is a good thing to do, or was it discouraging? Because I talked a lot about problems also.
It's awesome.
It seems to me like something you do in a functional language.
Yeah, but if you are tied to some language, of course it's very it's more natural in functional languages. But there are other weird stuff. Like if you have functional language and everything is immutable, right? And you need to keep somehow the state between the received messages in the actor. So what you do is that you call the same method in the loop with different parameters, and these different parameters are the changing state. Yeah, so it has some weirdness. But yeah, it's more usual in functional languages. Okay, some other stuff. I don't know, how much are you tired? I can skip this.
Go.
Okay, just this I found recently, and I found it very interesting. It's an atomic operation called compare and swap, and you can use it to replace mutexes, or let's say you have some variable and you are sharing it with many threads. So you would have to create some log over it and synchronize all the access to it. Or you can use compare and swap operation, which is atomic, and it works like that. Each thread is holding, let's say, the copy of the value. The thread is thinking that the variable is holding. And you do some stuff, and then you want to store something in the variable. So you call this operation, and the first thing is that you compare if the values are matching. And if it matches, it will store and it will swap the values for the new one. If it doesn't match, you will get false, and it's up to you to deal with that by computing the new value from the updated value. And there is a gem in Ruby called Atomic, and it works for MRI, JRuby, and Ruby News. And the interesting thing is that it's very fast. It's as fast as reading from an instance variable. If you use mutexes logs, it's 5 times slower. And that's the thing which is coming with the Ruby by default. So it's good to know about. And this is how would you update some, let's say, some counter. You create atomic new, which is just some reference to a value, and then you want to update, and this will be called over again until it will succeed, until it succeeds. Because if another thread updates the value, the compare will fail, and it will be computed again from the new value. Also, I didn't know that, but some of the data structures is in Java Uto Konkurenční package are using this to implement some data structures which are completely lock-free, no locks. It's all done with Konkurenční lock, which is very fast. So, very interesting. Java doesn't suck everywhere. Okay, and I think Ruby has event loops too, like twisted. And I just take it really fast. So as my colleague was talking about, in Ruby you can do this also. This is the example when you have callbacks everywhere, and if you need some another calculation when you get the response here, you would need to nest it in this block and you would grow indefinitely. It will be very ugly. But if you use fibers, which is the coroutines, or as in Python, you can wrap this, get the data method, and use the fiber to be yielding the result when it is ready. So in the end, it will simplify to just calling fiber new, which is creating the new coroutine, and then calling the get to wrap, and it will be walking until the result is ready. But it will be much lightweighted because the coroutines are much easy. It doesn't consume that much memory as threads. So this will actually allows you to do much more connections and handle much bigger loads of I/O operations that you will be able to do with just, I don't know, 100 threads. Just much faster and like that. Yeah, I also wanted to mention Vertex project, which is implemented in Java. But the interesting thing is that Ruby and Twisted event machine library for Ruby and Twisted for Python only have one event loop because the Ruby has GIL and Python has GIL, so you can't utilize all your threads. But Vertex allows you to do that because it's spawning multiple event loops for each core, but it has some interfaces to other languages, so you can actually write your applications in Python, Ruby, obviously JavaScript, Groovy, and use this under the hood and utilize all your cores. So it's quite interesting. It's not a very old project. And thanks for your attention. And do you have any more questions?